Ionization energy is the energy required to remove an outermost electron is from its gaseous atom or ion, its ionization energy. For example, X element in its gaseous state, and when you remove electrons, it's going to be X plus charge and the electron is going out, right? So we'll take an example for magnesium, Mg. So Mg plus 1, and we can take out one electron. So whenever the first ionization energy, we can say I1, and we can have 735 kilojoules per mole. And that's the first ionization energy, I1, first ionization energy. Now let's say that this one, Mg plus 1, we are going to remove the electrons again. So it's Mg plus 1, and it becomes Mg plus 2, and then we remove another electron, and then we have I2, that's the second ionization energy, and we have 1445 kilojoules per mole. Now let's say we are removing another one from this one. So let's say if it is, okay, let's say if we can, I'm going to write that one somewhere around here, Mg plus 2, and we are removing another electron, Mg plus 3, and that electron, and that ionization energy is called third ionization energy, and 7730 kilojoules per mole. So what that means, when you have first ionization energy, you require less energy. When you have second, third, you need more energy to remove electrons. What that means that, let's say you have nucleus here, okay, and your electron is here, here, and here. If you remove the first electron, alright, you need less energy because it's away from the nucleus. When you remove the second one, you need more energy because it started getting closer to the nucleus. Alright, so that's why second ionization energy is higher. And then third one, you need more pull on electrons, so that's where you need more energy. So that's why when you go from first to third, it will get higher and higher. Okay. Now when you look at the periodic table, what's its trend look like? You see that in the periodic table, metals and non-metals. And let's say if this is a zigzag line, this side is most of metals, and this side is non-metals. And you know that metals are losers, they lose electrons. Lose electrons easily. So if they lose electrons easily, and this non-metal has a characteristics of gaining electrons, right? So what that means, if these guys are going to lose electrons easily, what happened to the ionization energy? It's less, you need less energy to lose the electrons compared to this one. Ionization of energy of non-metals are higher compared to metals, right? So what's that trend look like? When you go from left to right, ionization energy what? Increases. So you can write that in general, as we go across a period from left to right, the first ionization energy, I'm going to write IE for ionization energy, it increases. That's the trend. Okay. Alright, so that's the thing. And the question is why. So we are going to learn why it is like that. Why the trend is increasing. So again, I'm going to write that explanation. Electrons added in the same principal quantum level do not completely shield the increasing nuclear charge caused by added protons. So you can see electrons basically in the same principal quantum number quantum level are generally more strongly bound from left to right. So what that means, and left to right on that periodic table. So for, let's see, if you have left to right, I'm going to find one. Okay, so let's say what that means. The same principal quantum level. In here I'm going to give you an example, lithium and boron. So when you write electronic configuration for lithium is what? 1s2, 2s1. Okay, and for boron 1s2, 2s2, 2p1. Now what that means, when you add electrons, these electrons are adding into this level, the 2p level, same quantum level, right? That means the number of the protons here, so let's say this is level 1, n equals 1, and this is n equals 2. Now you see this is 2 electrons here, 1 electron here. For lithium I'm talking about. And for here boron, we have level 1 and level 2. So whatever the level 2, number of electrons increases. Here it was 1, now we are increasing 3 here. But there is a protons here, pull on that electrons is increasing, right? So that's why you can say electrons are added in the same level, the 2p level.
What is it doing?
Electrons are added into the same principal level and it's strongly bounded.
Oh, okay.
Protons are added, so that's how you get more pull on it, and that's why you have more ionization energy on it. Okay, now let's talk about across it, going down the column. Now when you go in general, when you go down from top to bottom in a group, ionization energy increase or decrease?
Increase.
Decreases. Why? I'm going to show you. Let's say we are going to take alkali metal, okay, and we have lithium, sodium, potassium, so and so forth, rubidium, cesium, like that. And when you see that the N level, this is N equals, lithium is N equals 2, N equals 3, N equals 4, N equals 5, N equals 6. That means you can see rings levels are increasing, right? This is 3, this is 2. So levels are increasing. That means they are going away from the nucleus. The pull on that outermost electron is getting what? Lesser and lesser, right? So it's easy to pull out these electrons, right? So you need less energy to pull out those electrons, right? So that's why when you go down from top to bottom, ionization energy decreases, okay? So that way you can follow this trend. And I'm going to give you one example on all right. Example I'm going to write down here. Which atom would require more energy to remove electron? All right. Na or Cl and Na or Fr, and you can tell me. Reading the trend, remember when you go across it, across the period, ionization energy increases. So when you see which one is farther, sodium and chlorine, they are in the same level, they are in the same period 3, but chlorine is on the far
Side.
right. So what's the which one has a higher energy?
Chlorine.
Chlorine has a higher first ionization energy. Now when you look at the trend, when you go down from top to bottom in a column, which one is that? Sodium or francium?
Francium. Sodium.
Sodium, because francium has less energy, ionization energy, because it's in level 6, N equals 7, I'm sorry, N equals 7. N equals 7, so that means its electrons are on the 7th side, so you need less energy to remove it. So that's how you interpret those trends and identify ionization energy.